Hello everyone. Now we will discuss on the topic secondary treatment processes, and we will discuss in this class on secondary process for water treatment, types of secondary treatment processes, types of process and common name, Lagoon system, aerobic digestion, activated sludge process, anaerobic digestion, UASB, biofilter and microbial growth and retention time. Now, we will see what is secondary process. Already we have discussed in the previous class that after primary treatment the wastewater enters into the aeration chamber and we add microbial biomass there, the microbial seeds, we add microbes and then we get the conversion of organic compound and those are degraded in this secondary treatment step, and different types of living organisms can be used including bacteria, yeast, etc. Even plants and microalgae can also be used. So, secondary treatment processes are used after primary treatment process, which involve the use of living organisms for the following purpose, that is to degrade dissolved and particulate biodegradable constituents into non polluting end products, to remove or transform nutrients such as nitrogen and phosphorus, and to capture non settlable and suspended solids into a biofilm, and to remove specific trace organic compounds. So, this is the major objective of the secondary process, and there are number of types. We can classify this process into different types. So, based on air requirement, this can be aerobic process or anaerobic process, and in aerobic process this process takes place in presence of air and utilize aerobic microorganisms which use molecular or free oxygen to assimilate organic impurities, that is convert them into carbon dioxide, water and biomass, whereas in anaerobic process this process take place in the absence of air by the anaerobic microorganisms which do not require air or oxygen to assimilate organic impurities. The final products of organic assimilation in anaerobic treatment are methane and carbon dioxide gas and biomass. So, these are the basic two types, and if we see the type of living organisms we are using, on that basis it can be phytoremediations where plant species is used, and it can be phycoremediation when algae is used, or it can be bacterial process. So, biological treatment with microbes like say types of microbes may be bacteria, fungi, algae, yeast also, and when we will be using the microorganisms, because if we use bacteria it will be more preferable, its performance is better with respect to other methods. So, in that case the microorganisms may be in suspended form or may be in attached growth process, it can be in attached form, attached on some material, and that is called attached growth process. Now, we will see different conventional methods which are used in wastewater treatment like say Lagoon system, very simple one, and then aerobic digestion, activated sludge process, anaerobic digestion, UASB, upflow, anaerobic sludge blanket reactor and biofilter. So, these are the very commonly used methods as a secondary step for water treatment, and apart from this there are some advancement in the secondary processes also. Those are granular activated sludge process and sequential batch reactor. These two are the improved versions of the activated sludge process, and then membrane bioreactor and phytoremediation and phycoremediation and bioelectrochemical systems or microbial electrochemical cells. So, these are the some latest development in the wastewater treatment as a secondary treatment step, and we will discuss all these steps in few classes. Now, we will see types of process and their common names. So, if we go for aerobic process, so that may be suspended or may be attached growth as you have discussed, and for suspended growth different names are activated sludge process, aerated lagoon, stabilization ponds, aerobic digestion, and in case of attached growth we may see trickling filters, rotating biological conductors, packed bed reactors. So, these are very common names, but the process are basically under these two category. Then there are some hybrid process like suspended plus attached growth maybe, and like say trickling filters and activated sludge. And anaerobic process may be again suspended growth or attached growth and sludge blanket type, and the common names are anaerobic contact process, anaerobic digestion, anaerobic packed or fluidized bed, and upflow anaerobic sludge blanket, that is UASB. And lagoon different processes are also having the same common name like say aerobic lagoon, maturation lagoon, facultative lagoon, and anaerobic lagoon. Some lagoons are also aerated in some time, we will discuss that also. Now, this is a lagoon system. So, this is a low technology solution and very simple one. In this case, in the water microbes are present, algae are also present. So, algae will take the sunlight and they will produce food and they will produce oxygen. So, oxygen will be available in the water and oxygen also will be diffused from the atmosphere to the water through its surface. So, there is a two major source of oxygen in it in the water, one is to the diffusion from air to this water and another is from the algae. So, when algal cell will grow, oxygen will be available. So, at the top layer it will be in aerobic zone and at the bottom layer of the lagoon then we will see there is no oxygen. So, that will be anaerobic zone completely, and in between we will be having oxygen and carbon dioxide both. So, that may be termed as the facultative zone. Now, in this is the lagoon system. So, both aerobic, anaerobic and facultative reactions can be possible, and in this case say microalgal cells which are grown at the top layer, so at the bottom layer that will be after their death that will be decomposed also. So, from the bottom part methane, carbon dioxide and ammonia will be produced and from the top part oxygen is being produced. So, that way different types of phenomena will be going on, and this ammonia and phosphate which are produced here that will also be captured by this algal mass. So, this type of different types of reactions will be going on in the lagoon system and the organic compounds will be degraded. How this organic compound will be degraded? Because apart from this bacteria will also work on it. Again some algae are also there, they can take the organic as their food when light is not available. So, the in pond systems that is 1 to 2.5 meter deep we see, and detention time is 30 to 180 day and not easily subject to upsets due to fluctuation in flow rate and low capital operation and maintenance cost. Now, we will see different types of the lagoon system we can get. One is your aerobic, another is your aerated aerobic. Aerobic means as I mentioned the lagoon at the top part we are expecting that oxygen will be available. So, it may be possible that oxygen is available by the microalgae available in the water and through the diffusion to the surface of the water body. So, in that case we will be terming it as aerobic, but when we will be providing some additional oxygen, so that is aerated aerobic, that will be aerobic, but additionally some oxygen is provided. So, aeration of pond accomplished by use of mechanical oxygen diffusers. So, in that case we will be terming it as aerated aerobic, and aerated facultative that uses only surface aerators. Some anaerobic decomposition takes place in sediments at the pond bottom. That means, when we are providing additional oxygen, that can it is possible that we are providing the oxygen throughout the depth, or it may be possible we are providing the oxygen only at the upper layer, but not at the bottom layer. In that case, we will be getting aerated facultative. Similarly, for aerobic facultative and aerobic both condition we will get, when we will not be providing any additional oxygen by mechanical means, but the algae present in the water, those will be giving some amount of oxygen into the water, as well as by natural process air, from air oxygen will be diffused to the surface of the water. So, in that case oxygen supply provided at surface by algae and surface mixing by wind. So, some anaerobic activity in bottom sediment. So, basically 4 types of situations we are getting, and which phenomena is prevailing, that will depend upon the depth, and if depth is very less, certainly we will get the aerobic conditions, anaerobic area will be less, but depth is more, then more anaerobic area will be increased. So, we can get facultative in that case, and all these are having some advantages, like say relatively small volume, land area required, and odor free, high degree of treatment in case of aerated aerobic. And for aerobic, as oxygen is relatively less with respect to aerated aerobic, it is operation and maintenance cost is less, but performance may be lower, and aerobic facultative low operating and maintenance cost, high degree of treatment, and for aerated facultative relatively small volume or land required and relatively odor free, high degree of treatment. So, these are some characteristics of this type. Apart from that, we can get some disadvantages for all these type of systems as mentioned here, like in case of aerated aerobic, it is high operation and maintenance cost of any pond system, and in case of aerobic it requires large volume and land area with respect to aerated aerobic. So, there will be some scope for optimization, and labor requirement is also different for different type of lagoon system, energy requirement is also different. So, certainly when we are going for aeration, additional aeration, the energy cost will be more, and degree of complexity will also be more when we are going to send the compressed air at the bottom of the lagoon, and residuals will also be different as mentioned here for different cases. Now, we will discuss aerobic digestion. So, as the term indicates, oxygen will be available. So, there will be oxygen and waste, microorganisms will work on it, and their biomass will grow, synthesis, and then those biomass will be grown. So, more microorganisms will be getting, and there will be some respirations, and through the respiration some other elements will be produced. So, this is the reactions, different types of steps which occurs in case of aerobic digestion. Now, as you know that in presence of oxygen, some microbes are present, those can oxidize some metals, and they can take the energy released through this type of conversion for their growth. So, those are called chemoautotrophic bacteria and Gallionella ferruginea. This is aerobic and chemoautotrophic bacteria. So, by the presence of this bacteria, Ap2 is oxidized to Ap3 and energy is released, and that energy is consumed by this microorganism for their growth. Like similar way, Leptothraeoscracia, they also do the same job, but energy source is organic substrate. So, that is heterotrophic bacteria. Okay, these are some examples of aerobic digestion, and also many organic compounds will be oxidized in the presence of microorganisms, that is heterotrophic microorganisms. And basic ingredients and method which are required for this secondary treatment. So, those are high density of microorganisms, this keep organisms in system to ensure the high efficiency, and then good contact between organisms and wastes. Therefore, some aeration is provided basically for proper mixing and provide high levels of oxygen. For both the purpose oxygen plays a significant role. One, it provides the oxygen for the reaction, other way it also provides the mixing and good contact between organic compound and the microorganisms. And then favorable temperature, pH, nutrients, these are essential for the growth of the microorganism, because microorganisms are very susceptible to pH, temperature, etc. And no toxic chemicals should be present. If toxic chemicals is present, then the growth of microorganisms will be affected. So, the subsequent oxidations of the organic compounds will also be affected. Now, we will see the activated sludge process. So, in activated sludge process, our objective is to reduce the organic carbon present in the wastewater. So, our input will be inlet water quality, the facility dimensions and control conditions. So, these are very important to get the performance of this system. Let us see in this system what happens. In this system, the wastewater comes after primary treatment to the first tank, that is called aeration tank. Then in aeration tank microbes are also present in it. So, microbial degradation takes place. Then after certain residence time, the overflow goes to the sedimentation tank and then sludge are settled and supernatant goes for the further treatment, that is tertiary treatment, and this sludge, the part of it is recycled, and this is the source of the new microbial cells, and some part of the sludge is wasted and it is sent for waste management, sludge management. So, this is the flow sheet basically, and this is the process, activated sludge process. As the sludge is recycled for the activations or for the growth of the new cells in the aeration chamber, this process is called activated sludge process. And in this activated sludge process, our input is your wastewater after primary treatment, and then what is the influent quality and what is the dimensions of this reactor, this sedimentation tank, etc., and what are the conditions we are maintaining, that will give us some quality of the output, that will give us treated water quality and removal ratio. And there will be number of phenomena which will be going on inside these two reactors. So, there will be say phosphorus discharge, intake, nitrification, denitrification, and substrate hydrolysis, microorganism growth, DO supply and consumption. So, all those phenomena are very important for the successful operations of this activated sludge process. Now, this activated sludge process, in which a mixture of wastewater and microorganisms is agitated and aerated, leads to oxidations of dissolved organics. After oxidation, separate sludge from the wastewater and induce microbial growth. So, need food and oxygen, the microbials needs food and oxygen. So, those are provided also in the aeration chamber, and one mixed liquor suspended solids, that is equal to 3000 to 6000 mg per liter. So, somewhere it is 2500 to 4000 mg per liter is also sufficient. So, this MLSS that indicates the presence of microbial biomass in the aeration chamber. So, that is very important parameter to ensure the effective conversions of the organic compounds. Now, we will see anaerobic digestion. So, in this case oxygen is not needed. So, as shown here, influent is coming and then there will be some microbes. So, microbes will work on it in absence of oxygen. So, there will be some anaerobic reactions. So, carbon dioxide and methane will be produced. So, then after certain time of residence, so gas will be collected here and treated effluent will be going out from the top of this chamber. So, we see this is our sludge bed and this is our effluent collection zone, and in this case we see that CODs are converted to basically sludge and methane gas. Okay. That is our main objective, to get the methane. So, energy recovery is necessary from the anaerobic reaction, and then 10% of the COD is converted to sludge and 90% of the COD is converted to CH4. These are some typical values given for this upflow anaerobic sludge blanket reactor UASB. So, in this case normally higher COD concentration is necessary and at least 4000 mg per liter COD concentration is necessary in the influent water, then only this process can be used. Now, we will see biofilter. So, biofilter as shown here, so you see it has some influent here. So, that is pretreatment and this is biofiltration and effluent and some clarification. So, these are the different steps in the biofiltration process, and if we concentrate here in the biofiltration, then we see there are some media on which a film microbial film is grown, and in that film there will be some one side will be in contact with the bulk phase, that is organic present in the wastewater, and attached with this disc will be anaerobic zone and oxygen will be available in the water, and the microbes will consume the oxygen. The microbes will be attached on the disc media and consume the oxygen available in the water. So, at the water side more oxygen will be available, but when we will go towards the disc media, then the oxygen availability will be reduced. So, here aerobic and anaerobic both zones will be available. So, facultative condition will be available. So, it is one of the most important separation processes that can be employed to remove organic pollutants from air, water and wastewater. Any type of filter with attached biomass on the filter media can be defined as a biofilter, and the biomass will be attached on some media, and those different types of media have been used like say granular activated carbon, anthracite, filter coal, sand, bagasse, etc., and different shapes of the particles can be used as shown here. And then we will see the mechanism, how the biofiltration will work. So, in that case we see that some biofilm formation is necessary. So, attachment of microorganisms on the media, then growth of microorganisms, and then biofilm formations, and after certain time the microbes will be dead, and that is decay and detachments of microorganisms. So, these are the major steps or mechanism for the working of the biofilter, and we see the attachment of microorganisms. For the attachment of microorganisms need to be transported from the bulk of the solution to the surface of the filter media. So, that transportation of microorganisms, this can be done either by diffusion or by convection or sedimentations or active mobility of microorganisms. So, microorganisms itself can move from the bulk to the surface, or diffusion may help, or if there is any convection that will help, or the sedimentation can also help for the attachment. So, initial when it is coming, the microorganisms are coming at the surface of the media, then there will be some initial adhesion, either some van der Waals or DLVO. Van der Waals means attractive force and DLVO basically the repulsive forces. So, the two forces are available at the surface. So, depending upon the predominance, so initial adhesion will take place, and then film attachments. So, microbes have come to the surface, that depending upon the surface of the media, the attachment will be influenced. Like say surface properties, it has good surface properties, more heterogeneity, and then influent character, and the availability of sufficient elements which are favorable for the growth of the microorganisms, that will prefer the biofilm production. So, that film attachment and colonization, these two, initially the film attachment, then gradually it will grow. For this, these surface properties of the media as well as the influent character are both important. And then growth of microorganism. So, for the growth of microorganism, we need again the transport of substrate to biofilm, because microbes need organic compound for their growth, and those organic compounds will be degraded basically. So, from the bulk of the solution to the surface of the filter, it has to become, and that is by Fick's first law, transportation of the substrate can be possible, and diffusion of substrate into the biofilm. Then substrate which is coming from the bulk of the solution to the surface of the filter media, then it will be diffused through the biofilm, that is Fick's second law. And then microbes will also consume the organic compounds, and that will be guided by the many utilization kinetics like monod-like equations. So, here it is given Ritman and Brunner expression. So, there are different mechanisms which are followed for the growth of the microorganism, and then decay and detachment. So, after certain time microbes will be dead, and that has to be removed from the filter media, and that can be done by erosion, that can be done by sloughing, that can be done by grazing or predation or filter backwashing. So, we have also seen in the previous class that backwashing is necessary to remove the materials which is deposited on the filter media to avoid clogging. Now, there will be different types of biofilters like say packed bed, fluidized bed, rotating biological contactors and trickling filters. So, these trickling filters is very common and very primitive one. So, basically we see we have some media, and if we spray water for long term operation, if we use it for long term operation, so microbial film will be developed on the surface of the media and biological activity will be started and organic compound will be degraded. So, this is very primitive one, and then packed bed and fluidized bed, that can be developed by in case of by using different packing material and by the attachment of the microbes on the packing material. And in the rotating biological contactor, as shown here, you see this is our media where the microbes are available and organic compounds are also available, and this is our disc. So, there are a number of discs are there, that is side view. So, we are talking about one disc, and in this disc from the inside we are having some vacuum. So, water will be passing through this filter. So, microbes will be working on the organic compounds, and then organic compounds will be converted to CO2 and H2O, and this water after treatment, the water will pass through the surface of it, and in the surface we have biolayer formation. So, this microbes which will be growing on the surface, that will help to decompose the organic compound. So, this is the mechanism of the rotating biological contactor. Now, we will discuss microbial growth and retention time. So, as you know that when microbes, when we are adding some seeds, microbial seeds, so those will grow, and that growth kinetics can be defined as dx by dt, when x is the microbial biomass. So, dx by dt, and we know that this is a first order kinetics, and dx by dt is equal to mu x, but we also know that after certain time the some biomass will also be decayed or dead. So, that decay rate is also there. So, overall rate will be mu x minus k dx. So, that is by dx by dt, that is the overall growth kinetics of microbes in any medium or wastewater sample, and then this mu we can define, that is specific growth rate. So, this mu is equal to maximum specific growth rate into S by K s plus S. That means, the specific growth rate will depend upon the availability of the substrate in the media. So, by these expressions we can calculate the mu, and if we plot the specific growth rate, the value of mu with respect to K s, that is limiting nutrient concentration with respect to S. If we plot mu with respect to S, so this is S and this is mu. So, we will be getting this type of first order kinetics. So, maximum growth rate is mu max, and if we take the half value of mu max, then the corresponding S value is our K s, because in this expression if we put K s equal to S, then S by 2 S by 2. So, mu bar by 2, mu equal to mu bar by 2. So, that is the definitions of K s which is used in Monod function. So, by using these expressions we can mathematically calculate the growth rate of the microorganism, and for solid production rate dx by dt, that is related to substrate utilization rate dsr by dt, and dx by dt is equal to y into dsr by dt, and y is the yield coefficient. But if we net production rate we consider, that means if we want to include the decay rate also, then dx dt will be y into dsr by dt minus kd into x, where kd is the decay constant and x is the microbial mass concentration. And then by rearranging this we can get dsr dt equal to 1 by y into dx dt, and that is equal to this equal to mu x. In the previous slide we have seen that is equal to dx by dt equal to mu x, when we will ignore this one, only for growth phase we will be considering. In that case that this is converted to mu by y into x, or mu is nothing but mu max into s by k s plus s. So, ultimately dsr by dt is equal to mu max by y into x into s by k s plus s. Now, if this s value is much better greater than the k s, then we ignore this one, then we can get dsr by dt, that is equal to some constant, that is k mu max by y is equal to k into x, because in that case we will be having, we can ignore the k s. So, s will cancel, so that will be 1. So, mu max y into x. So, mu max by y we are considering it as k. So, k into x, this will be the expression. But if the s value is less k s, if s value is much lesser than the k s, then dsr by dt will be k into s into x by k s. In that case s is much less, so we are ignoring this. So, s by k s will be there. So, s by k s and k mu max by y. So, this will be there. So, we can k by k s is equal to k dashed. So, that mu max by y k s will be the expression. So, in this case we see that dsr dt dependent on x as well as s value, but in this case the dsr by dt dependent on only x value. Now, hydraulic retention time. So, hydraulic retention time, that is the volume by volumetric flow rate. For any case this is applicable. So, volume of the tank of the reactor divided by flow rate, and sludge age or mean residence time, this is defined as the mass of solids in the system divided by mass of solid living system per day. So, in this case if the V is the volume and x is the biomass concentration in it. So, x into V the total biomass present in it in the volume, and then if our x dash is the biomass it is living from the system, and q is the volumetric flow rate. So, this is the living of it, total x dash into q is the biomass living from the system. So, x V by x dash q, that is equal to our retention time, that is T. So, that is equal to x by x dash into V by q is equal to T HRT, hydraulic retention time. So, hydraulic retention time into x by x dash is our, that is sludge age or mean residence time or cell residence time. Okay. So, another important parameter which is essential for understanding the activated sludge process or secondary process basically. So, F by M ratio, that is substrate removal rate by solids or microorganisms in the system. So, this is our case x, and F is your SO minus S by T, that is the substrate removal rate. SO is the initial substrate concentration, S is the final substrate concentration. So, SO minus S by T the substrate removal rate divided by x. So, that is equal to SO minus S into x into T, and the capital X is nothing but small x into V, that is the concentration of microbial cell into the volume of the reactor. So, that way you can get the value of F by M. So, up to this in this class, thank you very much for your patience.